Before we start understanding what virtual memory is, which is a simple extension to your physical memory, because physical memory may not be enough for an average user, we implement a mechanism to extend that towards the hard drive. And before we understand that, let me first remind you what paging is. So you can see that we divide the logical memory into pages of equal size of memory, just like, for example, 128 bytes, 128 bytes, 128 bytes, 128 bytes, right? So we simply, without looking at the contents of the program, simply divide it into equal parts, and then we divide the physical memory, the RAM, in the same sizes of parts, in equal sizes, like 128 size, 128, 128, 128 bytes, each size with the same amount or the number. So we divide the physical memory into frames, and then we store these pages into physical memory into free frames wherever we find those free frames. Like, we could save this page 0 anywhere inside in this space. So here you can see that randomly whichever free frame this operating system found, it simply stored those page numbers here. Like, in frame number 1, page 0 was stored; in frame number 3, page 2 was stored; in frame number 4, page 1 was stored, and so on, right? And there is something which is called the page table, which we use to translate those pages into the frame numbers. So we can translate this page 0 into frame number 1, because page 0 is stored at frame number 1. Similarly, page 3 is stored at frame number 7. So on the fourth line of this page table, we which is actually page number 3, which is the index of this array or this list, on this index number 3, which represents page number 3, we write frame number 7, because frame number 7 is where page number 3 is stored, right? So this is how you implement paging. And paging is something which also allows us to implement virtual memory much easily. And virtual memory can be seen as an extension to the paging scheme over here. But I just wanted to remind you of all of this paging scheme. Now we go to the virtual memory thing. Virtual memory is an extension to paging in such a way that we say that we keep into the physical memory all the pages that are needed by that program at that particular moment, and we do not keep other pages inside the physical memory which we do not want at that particular time. So let me show you an example for that. So for example, if I start Microsoft Word, which we all use a lot. So this is Microsoft Word. You see that it is taking some time to load, and when I start a new document, the new document starts quite quickly. And this is where I type some things, and I can do basic stuff like changing the format of the font or paragraph or stuff like that. But if I go to an option which is less frequently used by me or by other people as well, seldom used even. So, for example, if I go to references and if I go to, let's say, yeah, so here you saw that it gave a message preparing search. So you saw there was a loading message over here for 1.5 seconds over here, loading, right? So this is one of the options which is built inside this application, but it was not loaded when I started this program. So this is the idea behind, this is the motivation behind virtual memory, that you do not bring the complete program into memory, and you only bring the program into the memory which is most frequently needed, and you bring the rest of the program uh, as per the need of the user, right? So this is the concept behind you know uh, virtual memory. So in virtual memory, we keep the rest of the program which is not currently needed by the user in the hard disk or the hard drive, which in this scenario we will call the backing store. So we keep everything in the backing store, and as the user needs or the program needs the pages, we bring those pages into the physical memory one by one, you can say. So that allows us to create as large a program as we think or we can think of. These are called virtual address spaces for those programs. So they can extend as many pages as we want. And then the physical memory, which is a limited size. So here you can see that the program is drawn in such a way that it is of bigger size as compared to the physical memory. Physical memory is smaller, and the program size is larger. This can be a real example as well. Why? Because maybe your operating system is only allowing a limited size to your program. So this is that memory which is maybe only allowed for your program, right? So in any case, there are two main things that we see over here. That, for example, now in this case the page table is like a memory map. When a page is needed and it is available in the physical memory, this is the arrow that represents this scenario or this case, and that will simply be available to your program. But what if a, a page which was referring to something which was not available in the physical memory, and that particular page was inside the hard disk? This is the hard drive. So what would happen then? So if that was the case, then your operating system will bring that page from the hard disk into the physical memory, and then that frame will be updated here, and then your program will get access to that page which was brought from the hard disk or from the backing store into the physical memory, right? So this scheme of virtual memory, although it takes into account frequently used pages, and it tries to store those pages in physical memory which are frequently used, which is I would say right now a vague description of all of this, because we only want to have those pages which are needed here and not frequently or less frequently used. But still, this example, this description can fit into this perspective. And when we say that a page is needed, only that page will be kept in the physical memory. So we are achieving something over here. What we are achieving is that, for let me give you an example. For example, there's a program, the size of that program is 200 megabytes, and right now we are only working, a user is using that program, and he's only using 50 megabytes of that program. The part of the program the user is right now using is only 50 megabytes in size. So what do we do? The idea here which is going on over here is that we keep the 150 megabytes the user is not currently using inside the hard disk, and we only keep the 50 megabytes that the user is currently actively using inside the physical memory. So what we are achieving using this scheme is that, for example, the memory could contain 10 programs of 200 size each. So if we are using 50 megabytes of all the programs, now how many programs can I accommodate in the same memory? Previously, I was accommodating 10 programs of size 200 each. So if I only keep 50 megabytes of each program in the physical memory, now I will be allowing 4 times the program. So now I can allow 40 programs instead of 10 programs in the physical memory, because each program is now only getting 50 megabytes in the physical memory, and those 50 megabytes are those megabytes which the user is currently actively using. So this is the idea behind virtual memory. Now you have allowed those 200 megabytes, 40 programs of size 200 megabytes to exist virtually, but physically only 25% of each of those programs is present in the physical RAM. It is simply a very simple concept, simple idea, that instead of bringing a complete program into the physical memory, you just bring in a small part of that program and you keep the rest of the program in the hard disk, and whenever needed you can bring in the rest of the parts. Let me show you an example for that. For example, these are your programs and this is your physical memory. How many programs can fit how many of these programs can fit into the physical memory? Let's say this one goes over here, and let's say this one goes over here. Only two programs, right? This is scheme number one. The second scheme is, why don't I divide this program into smaller sizes like these, which are pages, and I at one particular time I only bring in one of these parts of this program into this. So this part comes over here, this part comes over here, this part comes over here, and this part comes over here, and this part comes over here. Given the fact that I am only using actively, a user only actively use a tiny part of a program, now how many programs are in physical memory at the same time? 5. And I still have some space free. Virtual memory can be implemented in two techniques using demand paging or demand segmentation. We will be looking at demand paging. And demand paging is something when you swap in a program. Pure demand paging is something else, but one version of demand paging is when you bring in a program only when a program is needed. For example, if I minimize a program in this taskbar, that program is swapped out, and if I maximize a program, only then it is swapped in. So this will be called demand paging. So the user demanded a program, that program was brought into the memory, and this is called demand paging. Uh, Another version which is more popular is called the lazy swapper, which only swaps in a page when that particular page is needed. Instead of the complete program, it only swaps in pages. Slightly, only a part of the program is brought into the memory. And there are two cases when a page is needed by a program. The first case is that the that program is not even the in the logical space or virtual space of the program. That is, for example, if a program has 10 pages and it is making reference to page number 15, so that will be obviously invalid. So that is this case. The second case is that the page reference was valid, like it had 10 pages and it was talking about page number 7. This is a valid page reference, but that page was not right now available in the physical memory. Then you have to bring that page from the hard disk to the physical memory, and that is called demand paging. And many benefits of this scheme, but so now first let me for the implementation of demand paging, first let me describe to you what valid invalid bit is, and I will do it using this example. In this example we have a scenario which is where we have a page table, and there are two types of valid invalid bits. The first type of valid invalid bit we saw in the discussion of physical memory in the previous lecture, and in that we saw that there is something called a page table, and the page table translates the page number to frame number. So this page table is saying that page number 0 is located on frame number 5, page number 1 is located on frame number 0, page number 2 is located on page number 9, page number 3 is located on frame number 8, and let's just give it some number. So page number 4 is located on frame number 7 in physical memory. Now, because this page table is also a piece of data and it also needs to be stored somewhere in the physical memory, and the page size in the physical memory is 8. So when we store such a data structure inside the a fixed page size of 8 lines, you can say, then only 5 of these indicate or refer to, a page table. So in the last chapter, we saw that we use a valid invalid bit to differentiate the part of this page which holds the page table from the part of this page which does not hold the page table. So these valid bits are saying that only these lines are part of the, page table, and these lines are not part of the page table, right? Meaning that our program only consists of 5 pages. So I would like to ask you guys a question at this point, just to see your understanding of the paging scheme. Given this picture, what do you think? What is the size program? I'm asking, what is the size of our process in number of bytes or in number of lines? For example, this is one line, right? One line of memory. ये पेज टेबल ये बता रहा है कि हमारे प्रोग्राम के अंदर एक पेज है जिसका नाम है पेज नंबर 0, जो कि मेमोरी में फ्रेम नंबर 5 पे सेव हुआ हुआ है, लेकिन चाहे पेज हो या फ्रेम हो, उनका साइज हर एक का 8 लाइंस है, ये यहाँ पे लिखा हुआ है कि हर, और दूसरा नजर भी आ रहा है कि ये पूरा हमने एक पेज इधर बनाया हुआ है, ड्रॉ किया हुआ है, और इसमें 8 लाइंस है, 0 1 2 3 4 5 6 7। इसका मतलब है कि अगर एक फ्रेम या एक पेज 8 लाइंस का है और यहाँ पे एक फ्रेम की बात हो रही है, फिर दूसरे फ्रेम की बात हो रही है, फिर तीसरे की बात हो रही है, फिर चौथे की, फिर पांचवें की, तो हमारे इस प्रोग्राम के अंदर सिर्फ 5 पेजेस हैं जो कि 5 फ्रेम्स पे सेव हुए हैं, और हर फ्रेम का साइज 8 बाइट्स है या 8 लाइंस है, तो 8 × 5 वुड बी 40। तो ये इंफॉर्मेशन हमें बता रही है कि हमारे प्रोग्राम का साइज होगा 40। दूसरी चीज ये है कि ये वैलिड इनवैलिड बिट क्या बता रही है? दिस इज सिंपली टेलिंग कि इस पेज का कौन सा पार्ट पेज टेबल है और कौन सा नहीं है। दिस द अदर वैलिड इनवैलिड बिट इज यूज्ड फॉर डिमांड पेजिंग, and it tells the operating system which of these pages are physically present inside the physical memory and which of these pages are not physically present inside the physical memory. They are only part of the logical space which doesn't exist anywhere, but this is something we can visualize. So let me show you now the rest of this example. So for example, this is our physical memory. I have tried to draw a RAM over here. That RAM is divided into, the first 8 lines are frame 0, the second 8 lines are frame 1, third 8 lines are frame 2, frame 3, frame 4. These are all the frames in the memory. And right now you can see that page 1 is stored inside the physical memory. So in front of page 1 I have written, frame 0. This is frame 0, and I have used the valid bit to show that this page is inside the physical memory, page 1. Similarly, I have shown over here that page 0 is stored on frame number 5. So in front of page 0, I have shown valid bit to be valid, and in front of frame, I have written frame number 5. Similarly, if you go further down, you can see that frame number 8 is holding page number 3 of this program. So page number 3, frame number 8, and in front of that, you can see there is a valid bit which shows that these 3 frames, these 3 pages are inside the physical memory. Whereas for this page, page number 2, you can see there is an invalid I bit written over here. It means page number 2 is not in the physical memory, it is inside the backing store or the hard disk. Here you can see the hard disk, and page number 2 is located inside the hard disk. Similarly, page number 4, in front of page number 4, you can see the bit is invalid. It means page number 4 is also not inside the physical memory, it is inside the hard disk. And these numbers, they don't matter no matter what is written over here, because this valid bit is invalid. The frame numbers are now invalid. You can you can leave the previous number written over there, or you can simply ignore. You will never read those numbers because the valid invalid bit is invalid, and you will simply ignore those numbers. A pretty simple concept, that whichever page is physically present in the physical memory, you will use a valid bit, and whichever frame is not physically present in the physical memory and right now it is inside the hard disk, you will call it invalid, and you will use this bit to indicate which frames are there or not. So now we come to the second part, that is there a transition going on? Like for example, can this page go from the physical memory to the hard disk, or can this page go from the hard disk to the physical memory? So the answer to that is obviously yes. Transitions will take place. Pages will go from RAM to the hard disk for some reason, and they will be going from hard disk to RAM for some other reasons. So let me explain to you when and how. Whenever uh, there is less physical memory inside here, there are two reasons for that again. First reason is that all of your RAM is fully booked, fully occupied, and you don't have any free space. So you want one of the pages which were not frequently used or recently used, you can say, you want to push them out into the hard disk. This is the transition from RAM to the hard disk. Another reason for a page to go from here to there is that sometimes the operating systems don't allow more than a certain number of frames to a program. For example, an operating system has a policy that at any time your program can only have 10 frames of physical memory, not more. So if that is the case, then if for example, there is still free space, but still a page is pushed out because based on the policy, your program is not allowed to keep more than 3 pages in memory, for example. But your program wanted one of these pages inside the memory, so in order to bring one of these into the physical memory, you had to push this one out even if there was still some free space available inside the physical memory. So these are two reasons for the for a page to be pushed out into the hard disk or swapped out. So the reason for the other transition, the reason for a frame or a page to go from hard disk to the physical memory, this is simple. Whenever your program, for example, your program was executing in page number 0, so your program said that I need a data which is located in an address which refers to page number 2. Your program will simply make the reference. Operating system will see that the reference that the program has made, the logical address, it falls in page number 2, and then it will go to the page table. It will see that page number 2 is not valid, it is invalid, and it is not located inside the physical memory right now. It is located inside the hard disk. So it will first of all locate page number 2 inside the hard disk, and after finding that page, it will find a free frame inside the physical memory, and once it finds a free frame, it will bring or copy that page from the hard disk to the free frame. This is the method how we implement demand paging. So this is all of this that I have just described is explained much in detail using uh, this example. And by the way, whenever a page reference is made to a page which is not in the physical memory, which is invalid, and which is located inside the hard disk, this revelation, this finding out of the operating system that this uh, page is right now inside the hard disk, this process is called page fault. And whenever a page fault occurs, it simply says that the frame is not inside the physical memory, it is inside the hard disk.